Hello students, so this is a series of mass energy and nuclear binding energy of the chapter nuclei. This is an important topic for the CBSE NEET as well as the IIT examination. Let's begin this topic. The first topic is the mass energy. So students, as we know from the basics, like alpha particle consists two protons and two neutrons. Now, what is the alpha particle? Alpha particle is a nucleus, helium, nucleus. Okay, when this helium particle is a element is heated up, the radiation start to emit. These radiations are alpha particles actually, and these alpha particles have two protons and two neutrons. Now the mass of the actual alpha particle in the AMU, or we can say in a unit, that is a 4.0015. In the terms of a proton, we are saying that mass of alpha particle is a 4 times mass of proton. In a kg, that will be 1.67 10 to the power minus 27. Like these 4 times in the mass of a proton, the mass of alpha particle is actually. The total mass of the individual particles is a 4.0320 unit. And the difference between the above two masses is due to the binding energy of the alpha particle. What is this mean of that? I just want to explain over there. Like if we have a nucleus, okay, nucleus have a random shape. So I'm just taking a nucleus, and that nucleus have one proton. If I'm just taking the hydrogen particle, but here I'm just taking alpha, so two proton and two neutron. So what will be happen? Like in the experiment, it will be assumed or it will be observed actually that if we are just taking the combined mass of the nucleus and individual mass of the proton and mass of the neutron, if I just do sum up of that, so that must be equal, but it's actually not came in by the experiment and by the result. What it came, mass of the complete nucleus is less than the individual masses of a both one. So the scientists were thought that how it will be happen. Like the mass of the complete body is same. If I'll just give a simply energy to break that particle, mass suddenly varies. So why this variation comes? So because of that, Einstein came and gave their famous relation, which is a mass energy relation. And according to that, if I just give to the energy of any system, any substance, so that energy will be converted itself into the mass. And that mass we are saying as a defective mass or a mass defect. We are saying as a mass defect. So that mass defect is represented as a delta. I hope you understand, you students. Now for the alpha particle, delta M is equals to minus 0.0305 unit, and the binding energy will be minus 28.4 mega electron volt. The alpha particle has a lower energy than a collection of a separation of proton and neutron. Since the proton in the nucleus are charged particles, they have potential energy associated with them. This is very large compared to the typical atomic scale energy of around 1 electron volt. Students, electron volt is also unit of energy, and the value of a 10 electron volt is simply 1.6. If I just want to convert 1 electron volt into joule, this will be 1.67 10 to the power, or simply 1.6 only. There is no need to write 1.67. So 1 electron volt is equals to 1.6 10 to the power minus 19 joule. Similarly, if I just want to do apply, like if I just do apply with the 10, So what answer came? 16 10 to the power minus 19 joule. This is actual energy which is came from the atomic scale energy. This is much larger. The energy is associated with the electron molecules and the chemical reactions. What we observed, students, that electric potential energy of a proton in the nucleus is of the order of a mega electron volt. Have you know the meaning of a mega electron volt, student? Mega means 10 to the power 6 electron volt. So that potential energy is 10 to the power 6 times stronger. The potential energy associated with the strong force is a negative. So where there will be a strong force connected, there must be came negative sign. That negative sign shows the force of attraction and also the order of a mega electron volt. The rest energy of proton and neutron found to be E is equals to mc square. And for proton, this will be 938 mega electron volt. Mass can be expressed in the unit of energy per speed of a light square. So the mass of proton for that scenario 938 mega electron volt per speed of a light square or c square. Mass can also be expressed in atomic mass unit, which is a U. So 1 U is equals to, as I told you, 1.67 10 to the power minus 27 kg, which is in mega electron volt 931.4 mega electron volt per c square, student. This formula is a very important formula for the CBSE exam. CBSE exam, or you can say your board exam. For the NEET, IIT JEE, as well as for the advanced level. Okay, so this is a very important formula because in the nuclei there must be one question came. So what we conclude from here? The conclusion is simply which we did. That conclusion is simply the mass energy relation and the mass energy. So according to the Einstein, mass and energy are inner convertible. That means the mass can convert in the form of energy, or we can say, if I'll just give energy to the system, that will be stored in the terms of mass, and that formula we can calculate it E is equals to mc square. And from here, two particular things came into the nature: pair production, pair annihilation, nuclear stability. Pair production, pair annihilation, nuclear stability. Principle of equivalence. According to the principle of equivalence, it is proposed by Einstein. The energy equivalent to the mass m is given by E is equals to mc square, and the mass equivalent energy E is given by m is equals to E by c square. So the principle of equivalence is used here to estimate the binding energy of the nucleus. The binding energy actually the minimum energy by which the nucleus can break. To estimate the energy released in the nuclear reaction, that how much energy actually released after nuclear reaction, there will be many nuclear reactions occur in the nucleus. So that value is known as a Q value. Now move some questions so that we can understood, like whatever I just taught you, that you have understood or not. So first question is, the principle of equivalence is used. The first one option, to estimate the binding energy of the nucleus, to estimate the energy released in the nuclear reaction, only A, both A and B. So the correct answer for this question is both A and B. To estimate the binding energy of the nucleus and to estimate the energy released in the nuclear reaction. Next question we have, one atomic mass unit is equals to, we have these options. Now the correct answer for this question is a 1.66 10 to the power minus 27 kg. Next topic we have mass defect and binding energy. Nuclear binding energy. For stable nuclei, we know mass of the nucleus containing N neutron and Z proton is a less than the total mass of N isolated neutrons plus Z isolated protons. That means the mass of the nucleus is always less than the sum of the constituent nucleons, their masses. As I told you earlier, that difference is known as a mass defect. Okay. How we will calculate? We just do the complete individual masses of the nucleons. Just do sum up and take the complete nucleus and do subtract from both. There will be a term came which is a delta M, and delta M is that difference of a mass which we call as a mass defect. Okay. So the energy equivalence of a mass defect is called as a binding energy, or very simple way, that is the minimum energy required to break that nucleus part is known as a binding energy only. The binding energy can be found by binding the mass of the nucleus and then subtracting the mass of the same number of isolated proton and neutron itself. Binding energy of the nucleus is given by Be is equals to delta M times c square, where delta M is a mass defect and c is the velocity of a light. Binding energy is in erg, where delta M is in gram and 9.9.0 10 to the power 20. So what is the erg actually? Erg is a SI or CGS unit of the energy. Okay, and joule is the SI unit. Gram, again, CGS system. So we know that like mass into c square. So binding energy mass into c square means 3 into 10 to the power 8. So 8 square comes 16, and because we are taking the terms in our arg, so that's why we are taking 20 over here. Student, don't be confused. This is a c square actually. And what is c? Speed of a light. And when we are taking a speed of light, okay, and when we are taking CGS system, so we know that we are using the term in the centimeter, and 1 meter is equals to how much centimeter? Yes, of course, this is 100 centimeter. So instead of a 9 10 to the power writing 9 10 to the power 9, because 8 8 16, so what we are writing like m squared. So I have to convert this into centimeter also now. So for that scenario, 10 to the power 2 for the 1 terms, and for the 10 to the power 2 for second term. Now this will be converted totally into the centimeter square. 10 to the power 10 to the power 2. What it's come? 10 to the power 4. So 10 to the power 16 plus 4. That's why I wrote here 20. I hope you understood, students. So this is a CGS term which we are taking over there. And this is what SI term. SI. Okay. So because of that, the binding energy in joule, that will becomes delta M is equals to kilogram 9 10 to the power 16 over here. I hope you understand, student. If there is any confusion, you can ask your question in the chat session. Now, if the mass defect is a delta M is in AMU, then the binding energy is a 931.5 mega electron volt. This you can calculate by the help of a binding energy formula if you know the value of a mass defect. How you will be calculating the value of a mass defect? So student, for that, what you have to do, simple things is that just calculate the individual mass of proton plus neutron and do negative with the complete mass of the nucleus. This gives the value of a delta m. C, you know, students, that will be 310 to the power 8 in a SI unit. So what you have to do, because C square there will be came, so just solve it to 9 10 to the power 16 came into the nature. Just put all these value and you will be get easily the formula, the value of a binding energy for a particular alpha particle, which is a 931.5 mega electron volt. I hope there is a no kind of issue. If Z and E respectively represent the atomic number and a mass number of the nucleus, then the binding energy of the nucleus is given by binding energy is equals to Zmp plus A minus Zmn minus m nucleus times C square into the joule. So what I did, I simply taken the individual, see, number of proton is present, which is showing Z, mass of proton mp, A minus Z neutron, okay, number of neutron, Mn mass of a neutron. This is the individual masses of these elements, okay. And again what I did, just minus 2 with the nucleus. So this is the value comes delta m. And we know binding energy is delta m into C square. So I just put this value over here. Okay. Now, where mp is the mass of proton, mn is the mass of a neutron, where m is a stable nucleus. And binding energy per nucleon is known as the binding energy per nucleon A. Packing fraction now, like previously, that would be the important topic, but right now that packing fraction questions not came simply. That is the delta m by A, where A is atomic weight, means you can say that the rate of a change of atomic weight with respect to the atomic mass in AMU. If the packing fraction is a negative, then nucleus is a more stable. And if the packing fraction is a positive, the nucleus is unstable. And if the packing fraction is 0, so that is only applicable for the carbon, that is 6C12. Now we are going to start the topic binding energy curve. So let's begin. So the next topic is the binding energy curve. The curve obtained by the plotting the binding energy per nucleon versus the mass number is known as the binding energy curve. So here we are just drawing to start, like if I'm just taking the mass of the element m, so to destroy that particular element or to break that particular element, to find the value of a number of proton and number of a neutron, we need some kind of energy. That energy is known as binding energy. The minimum energy required to break the nucleus, this is known as a binding energy. So that binding energy versus the mass number graph is known as binding energy curve, like this. Why this binding energy curve failed? So the main failure of binding energy curve, binding energy is a high to the large value, like the value of A is between 28 to 138. Light nuclei such as a hydrogen combine form of a heavy nucleus for a greater stability. This process is known as nuclear fusion. Means if just I want to give the like high energy to the hydrogen atom, so the value of a nucleus, actually the nucleus start to fused. For this process is known as a nuclear fusion. Heavy nuclei, which is a actually mass number is greater than 220, are highly unstable. Highly unstable means they will be randomly start radioactive decay, like alpha particle, beta particle and a gamma particle. Beta particle also for the two types of a decay, beta plus decay and beta minus decay are there. So when they breaks into nearby equally nuclei, they are stable. Understood? Means they are continuously radiated till that when they are stable position. If they get a stable position, they are neutralized. Okay, so we are just taking heavy nuclei if like a lead. Okay, so they will start like uranium 238. They will start to radiate their energy in the form of alpha, beta, gamma rays. After radiating such kind of energies, they will becoming stable. After gaining the stability point, they just gain their stability point, and this process is actually known as we are saying as a nuclear fission. So in a nuclear fission, the particles are basically stabilized. The most stable nuclei are those which have a largest binding energy. Okay, near that Fe, as I told you, iron and nickel with A is equals to 56. With increase the mass number, binding energy per nucleon first increase. Okay, then after reaches the maximum value, like as I told you, iron 26 Fe56, the maximum value of binding energy per nucleon is about 8.8 mega electron volt. Thereafter, with increase the mass number, binding energy per nucleon decreases very slowly to about 7.6 mega electron for uranium 238. So very light nuclei are the least stable. Very high nuclei are unstable. The nuclei with the intermediate mass number are most stable. And the decrease is the binding energy per nucleon of the heavy nuclei due to the electrostatic repulsion between the protons. Binding energy per nucleon for a helium is about 7 mega electron volt. For this scenario, nuclear fission is possible with the release the energy. And that's why we are saying helium is the most stable. And if the value of A is less than 20, then nuclear fusion is possible with the release of energy. For that scenario, students, nuclear energy is released in the fission form because the binding energy per nucleon is greater than the fission fragments. And that is the initial heavy nucleus situation. So minimum are associated with the nuclei containing an odd number of a proton and neutrons, such as we have a tritium, which is a like form of a hydrogen, which is a 1H3. Boron we can let's take as a 5B10, and neutron we can take the 7 and 14. So the maxima associated with the nuclei having the even number of proton and neutrons, such as a 2He4. Like helium has a 2 proton also, as I told you, number of proton plus number of neutron, which gives the mass number actually, which is a 4. C612, O6, 8, O6, like this. So in this nuclear fusion process, energy is released, and because of the binding energy of the heavy nucleus, they found some research and result like fusion is a greater than total binding energy of the lighter nuclei. So what we conclude the result? Fusion is greater than the total binding energy of the lighter nuclei, which they actually fused. So iron, whose binding energy per nucleon stand maximum, which is 8.7 mega electron volt, is the most stable and will undergoes neither fission or nor fusion. Let's take some question for more understanding that whatever I taught, have you understood or not? The difference between the mass, the first question is the difference between the mass and the nucleus and the total mass of the constituents is called packing fraction, binding energy, mass defect, mass energy. The correct answer for this question is a mass defect. Next question we have, if capital M is the atomic weight and capital A is the mass number, then M minus A by A represent mass defect, packing fraction, binding energy, chain reaction. The correct answer for this question is a packing fraction. Force inside the nucleus. So student, if I'm just talking about the forces which is occurring inside the nucleus, is a nuclear force, Coulomb force, tensor force, and a hardcore repulsive force. These four forces are actually working in the nucleus. Coulomb force. is the force of repulsion between the proton and another proton. These forces are responsible for instability of the nucleus. As the atomic number increases, Coulomb force increases and stability of the nucleus decreases. For example, like C612 is stable, but 92U235 is unstable. So as the mass number increases, continuously the value of instability increases. Next, the forces which are acting within the nucleus or among the nucleus is called as nuclear forces. Nuclear forces are much stronger than Coulomb force or a gravitational force. So nuclear force between the two nucleons falls rapidly to the zero because of their distances is more than femtometers. This leads the saturation condition for the forces. Now, repulsive forces are between the proton is about 10 to the power 36 times as that great as the gravitational force between them. So if I'm just taking the strength-wise ratio like gravitational, electrical and nuclear, so that will be 1 ratio 10 to the power 36 ratio 1 10 to the power 38. Properties of a nuclear forces is a simple because we know about few things about the nuclei, like they are very strong in the forces that's why we are saying strongest force in the nature. Charges charge independent, they are not depending on the charges like proton force, neutron force or proton neutron forces. Short range because the nuclear forces are applicable only the separation of a nucleus, which is the order of 10 to the power minus 15, which we are saying femtometer. Spin dependent nuclear also have dependency on the spin. Nuclear forces are the strongest if the spin of the nuclear are parallel. Non-central. The nuclear forces does not actually act at the line joining of the center of the nucleons. Non-electrical, non-gravitational, exchange forces. So nuclear forces is due to exchange of a pi meson between the nucleons. So we have basically three types of mesons are there: pi plus meson, pi minus meson, pi zero meson, which is predicted by Yukawa theory. So like P, if I just want to take a reversibility symbol, so P reversibility n plus pi plus, and n reversibility will be P plus n plus pi minus. Again P plus P gives out like a reversibility symbol n plus pi 0, and n plus reversibility sign n plus pi 0. Nuclear forces show the property of a saturation. A nucleon does not interact with all other nucleons, but yes, only limited number of them, which are actually nearest to it. Next one is a hardcore repulsive. So if the distance between the two nucleons becomes less than 0.5 femtometer, there is exist a force of repulsion instead of attraction. So these forces are called as a hardcore repulsive forces. Now they are strong repulsive forces, and these forces keep the volume and density of the nucleons constant. Tensor forces. So all the nucleons have some spin. So they behave as a magnetic dipoles. And there exist are a force between two dipoles, which is called as tensor forces. It is an attractive forces. It prevails up the distance of 3 femtometer. Tensor forces arises due to the spin motion of the nucleons. Beta decay is mainly for the tensor forces. Any nuclear reaction involves in the conservation of a mass, energy, charge, number, linear momentum, angular momentum like this. So let's move with this question part so that we I can understood, have you understood the things which I taught or not? Which of the following is not correct about the nuclear forces? They are short range attractive forces. They are independent of the charge. They changes the repulsion at very close distance. They obeys inverse square law. The correct answer is D. They obeys inverse square law. Next, nuclear forces between a proton and a neutron are between the two neutrons are respectively FPP, FNP, and FNN. Then F here is a few options are given, and the right option is 3-1. Like all these forces are equal. So students, these all these things about for the today's class. I hope you like the session. If there is any kind of like confusion, you can ask the things in the chat session. Till that, take care, students. Thank you for watching this video.